All right, welcome back. Today's lesson is methods of counting. All right, and we are on page P11 of the textbook. And I always tell students this is a hard lesson. No, not really. Okay, this lesson is actually kind of simple, but I will say this. The concepts that we're going to learn, okay, when we start digging deeper into these concepts, can be very, very challenging. Maybe say it like, it took me years, okay, it took me years to visually or spatially understand what was happening here. It's not something that's intuitively obvious. But with practice, you guys can become very, very good at this. But let's start with, first off, we are multiplying, not adding. Multiply, not adding. Now, when you multiply, things get big very, very, very quickly. Let me say this. You have 21 students in a room, okay? How many ways can you choose 3 students out of 21? How many ways can you choose a group of 3 students out of 21? This will blow your mind, okay? I ask this question a lot of times. I get the answer of 7. 21 students in a room. You're choosing 3, and it makes sense to say, well, 21 divided by 3 gives 7, but the answer is actually 1,330 ways this can happen. You have 21 students choosing 3, 1,330 ways this can happen. Wow. Okay, so hopefully, okay, watch this. Here, you have sweatshirts. We have to establish that we are multiplying, not adding. You walk into a store, all right, you have large, medium, small to choose from. Okay, you have color red, color blue. Okay, you have 3 sizes, 2 colors to choose from. Okay, now to establish that we're multiplying, let's look. Well, you could choose a large size and color red. You could choose a large size, color blue. What else could you choose? You could choose medium, color red, medium, color blue. You could choose small, color red, small, color blue. So count it. 1, 2, 3, 4, 5, 6. Again, we are what? We are counting. 1, 2, 3, 4, 5, 6. We established there are 6 ways we could choose a sweatshirt. Okay. Notice, how many options did we have for size? Okay, we had 3 options for size, and we had 2 options for color. Okay, 3 multiplied by 2 gives a total of 6. So the key is we are multiplying today, not adding. 3 times 2 gives 6. Now let's generalize a little bit here. Okay. So diagramming, what I just did here, writing it out is what I mean by counting. You're actually writing it out and figuring out your number of different options here. That's how you're going to start to understand this stuff. Okay, so 3 sizes, 2 colors. Now I'm going to say we have 4 styles. Okay, so what would we do here? 3 sizes, 2 colors, 4 styles. We would still multiply. We would have 3 multiplied by 2 multiplied by 4 gives a total of 24 different sweatshirts. Does it matter if we add another category? No. Could we still diagram this? Yes. Okay, so we have 3 times 2 times 4. So 3 sizes, 2 colors, and now we add in 4 different styles to choose from. Well, after you choose 6 different size color options, you could then have 4 different styles. You could combine that with 4 different possibilities for style. 3 times 2 times 4 is 24 different sweatshirt combinations. We call this independent case. So today you will be not only solving, but telling me whether this is independent or dependent case. Okay, and you said, what are you talking about? Well, I'll show you in a minute. Okay, let's go over to this problem first, and then you'll understand the difference. So let's look at this question. It says there are 8 students in a spelling bee. How many ways can first, second, and third place be awarded? Okay, how many ways can first, second, and third place be awarded to 8 students? Well, this is how we're going to do it. Okay, you have first place. I'm just going to show you how to do this. First, second, third, then we're going to try to understand it. Okay, first, second, third place. Now, you have a total of 8 students in the spelling bee. So my question is, how many students are possible, assuming we choose first place student first, how many options do we have for first place? Okay, so we're looking at these 8 students. We're going to choose a first place. Okay, so we have, 8 options for first. Now, after we choose first place, the concept is the person that is awarded first cannot achieve second. Okay, so after we choose first place, now how many options do we have for second place? No, remember, the student's out, so we only have how many options? 7. Okay, and after we choose first and second place, okay, 2 students are now out. How many options do we have for third place? We only have 6. 8 times 7 is 56 times 6 is 336. 336 different ways to award the prizes. Different ways to award prizes. So, 336 ways to award the prizes. Wow, 8 students, 336 ways. This is called dependent. What do I mean? Okay, well, if we start with the dependent, you'll understand the independent. Okay, so dependent. Why? Depends on. Dependent means depends on. So if we look here, question, after we chose first place, we look to second place. Did our choices for second place depend on who was chosen for first? Yes. Okay, after we choose first and second place, okay, 2 students are out. Did our choice for third depend on who was chosen for first and second? Yes, okay, because we are eliminating possibilities as we go. So we choose first, we choose second. We only have how many options for third? We only have 6. Does the 6 options for third depend on who was chosen for first and second? Yes, we call this dependent. And over here, this is called independent because after you choose a size of sweatshirt and you go to choose color, okay, for instance, if you chose a large size, okay, and now you have red or blue to choose from, do you still have red and blue to choose from no matter what you chose for size? Yes. Does your color choice depend on what you chose for size? Not at all. Okay? You choose a large size, you still have red and blue, assuming the store is fully stocked. They're not out of any sweatshirts. We're not assuming they're out of sweatshirts. So the emphasis is after you choose your size, do you still have 2 colors? Yes. And after you choose your size and color, do you still have 4 styles to choose from? Yes, assuming the store is not out of inventory. So they call this independent case because the second choice, your choice for color, does not depend on what you chose for size. Okay, so these are called mutually exclusive events. Okay, now, ever wonder, this bothered me, I lost sleep over it, how many, well, you lose sleep until you decide to just solve it. Are we running out of license plates? Are there enough license plate numbers to go around to the entire population of the world? A lot of people drive, not every person drives, but are there enough license plates out there for us so that we don't run out? Well, yes. My first question is here. How many numbers are there from 0 to 9? Okay, we have to establish this first. How many numbers are there from 0 to 9? If you say 9, that's not correct, guys. There are 10 numbers from 0 to 9. Well, why? Well, let's show you. From 1 to 9. From 1 to 9, there are 1, 2, 3, 4, 5, 6, 7, 8. There are 9 numbers from 1 to 9. Now, if we add a 0 into this list, we have a total of how many options? 10 options. So there are 10 digits from 0 to 9. That's going to be super important for concepts that are coming in this class. So how many numbers are there from 0 to 9? There are 10 digits, or 10 numbers from 0 to 9. Now, on a license plate, so you call the DMV, you're worried about this. There are 7 spaces on a license plate. Okay. Now, we can have letters. Okay, we can have letters. So I need you to tell me how many letters are in the alphabet. Well, there are 26. And we can also have digits. Digits 0 through 9. So how many digits are there from 0 to 9? There are 10. So how many options do we have for digits and letters on the license plate? 26 plus 10 gives a total of 36 options for letter or digit. Now, there's other things that kind of go on a license plate, like a dash, an ampersand. There's other things, but we're going to just ignore the symbols. Okay, we're just looking at letters and numbers. So this is actually a smaller outcome than it's actually possible, because there's other things that can go on a license plate, but just letters and numbers. Okay, if we just had letters and numbers, do we still have enough license plates? Okay, so question, if we have A on a license plate, can we have A again? Yes, and if we have AA, can we have A again on the license plate? Can letters repeat? Yes, okay, so if we have A, we can still have A. So how many options for the first letter? Okay, so you have not just A, you have B, you have C, you have any digit. So we have 36 options for first letter or digit. Now, since they can repeat, if we chose A for the first, can we still choose A for the second? Yes. So how many options do we have for the second? We still have 36. And can we repeat again? Absolutely. So we have 36 times 36. How many options for the third? Still 36. Still 36. Still 36. Remember, are we adding or are we multiplying? We are multiplying. So 36 times 36 times 36 times 36 times 36 times 36. This is equal to 36 to the 7th power, which is equal to about... This is equal to about 78 billion. Okay, it's actually more than this, but around 78 billion possibilities for license plates. Now, there's only 7 billion people in the world. We can rest at ease. Okay, yes, there are enough license plates out there. Okay, so definitely not running out of license plates, guys. There's 78 billion. Now, let's just, we call this, did our second choice depend on what we chose for first? No, we call this an independent event. Why? Well, because this first choice does not affect the second. Independent, I can never spell when I'm writing quickly, independent event. And look at this case, 1, 2, 3, 4, 5, 6, 7. Okay, so let's look at the case where assuming if we choose A, we can no longer choose A again. So if you use A, the rules are if you use letter A, you cannot use it again. If you use digit number 9, you can no longer use digit number 9 again. Okay, so my question is, how many options for the first? We have 36. Now, assuming you chose A for the first, you can no longer choose A for the second. How many options do we have for letter 2? We know this is not correct. We know that numbers and letters can repeat. But I'm just saying a what if. This is a what if. What if the rule was we could not repeat on the license plate? Okay, so if you choose A for the first letter, the DMV says, nope, can't use A again, so you have to find another letter. So if you choose, okay, you have 36 options for your first choice. Now how many options do you have for your second? You only have what? 35. Again, we are multiplying. Now, after you choose the first letter and the second letter, for instance, or digit, say you chose an A for the first and you chose a letter, or say digit 7 for the second, A7. Okay, how many options do you now have for the third? Well, you chose A, you chose 7. You can't choose these anymore, so how many options? You only have 34. Okay, does our third choice depend on what we chose for the first two? Yes. Okay, so 36 times 35 times 34 times what? 33 times 32 times 31 times 30. This is actually around approximately 42 billion. So do we still have enough license plates? Absolutely. Even if things could not repeat, we've got plenty enough license plates. There's only around 7 billion people in the world. So looking here, we call this, did our second choice depend on what we chose for the first? Yes, we call this dependent case. Okay, again, because the second choice depends on what we chose for the first, and our third choice depends on what we chose for the first and second. So again, dependent. Okay, our choices are, notice the values are what? Decreasing. Okay? Notice with independent, the values stay the same, or they're independent of one another. Now, let's go to page P11. Or actually, before we do this, maybe give you a quick little example of replacement. I have 3 pens in my hand. Okay, 3 different colors. I got pink, purple, and silver. Okay, so I'm looking at 2 draws here. We're going to draw a pen, and then we're going to draw another pen. This is with replacement. Okay, so first we're going to do with replacement. So I have 3 pens in my hand. I have pink, purple, and silver. Okay. Close my eyes. Question, what's the probability of drawing pink? Hopefully you say, well, there's only 1 pink. There's 3 pens total. The probability of drawing pink is 1 out of 3. So the odds aren't very good. If I draw a pen, drew silver. Okay, put it back in. Drew silver again. Okay, so put it back in, drew purple. Okay, so I still haven't even drawn pink yet. So the odds, we call that probability. That's a different topic, but very related to this, okay? What are the odds of drawing pink? Well, 1 out of 3. Now watch this. So close my eyes. I have 3 pens to choose from. So what is my total options for the first draw? There are 3. Let's write that on the board. There are 3 options for the first draw. We're going to call this the first draw. We're going to call this the second draw. Okay? There are 3 options for the first draw. 3 options for the first draw. Okay? So now, close my eyes, I draw a pen. Chose pink. Now, I'm going to take the pink pen and I'm going to replace it. Notice I wrote with replacement. I'm going to put it back in. Now we're going to draw a second time. Okay, close my eyes again, close my eyes. Okay, drew silver. Okay, so how many options did we have for first draw? Well, we had 3 options for first draw. Since I took it out, okay, looked at it, then replaced it, how many options did I have for the second draw? I still had 3 options for the second draw. So we have 3 options for the first draw, 3 options for the second draw. My question is, did the second draw depend? Did our choices for second draw depend on what we chose for the first draw? No, because we replaced. 3 times 3 gives a total of 9 different possibilities for different types of draw combinations that we could have had. Now, okay, let's put this together here. So let's look at a different case. Let's look at without replacement. So without replacement, okay, first draw, second draw. First draw, second draw. So again, without replacement. So here, how many pens do I have for first draw? I have 3. Okay, so I close my eyes, grab one. Got pink. Now I throw it away. Okay. Now how many options do I have for second draw? Okay, I close my eyes again. How many options do I have for second draw? If I did not replace it, did not put it back in, how many options for second draw? I only have 2. Okay, so I could choose, I got silver. Okay, so for first draw, I had 3. For second draw, I just had how many? 2. Okay, for a total of 6 different combinations that could have happened. Okay, the first one, with replacement, did our second choice depend on our first? No. But without replacement, did our second choice depend on what we chose for the first? Yes. Okay, so with replacement is called independent because the second choice was not affected by the first. Without replacement, the second choice did depend on what we chose first because we threw it away and we only had then 2 options to choose from. This is called dependent. So hopefully that kind of gets you guys thinking in terms of independent, dependent. Okay, if I misspell, I tend to misspell because I'm rush and I don't pay attention. And so if I misspell a word, just forgive me for that. Sometimes I don't always catch my mistake. All right, now, let's look at the problems in the book. Page P11. Okay, the first problem says, how many ways can you do your math homework, your chemistry homework, and your English homework? We're looking at number 5. Okay, so page P11, number 5. How many ways can we do math homework, chemistry homework, and English homework? Okay. Now, what we're going to do is diagram this. I think diagramming it makes it come to life, and then we're going to talk about calculating it, whether this is independent or dependent. So let's think. You have math, chemistry, English homework. You go home. How many ways can you do this? Well, could you do your math first, your chemistry second, your English third? Yes. Could you do math first, then your English, then your chemistry? Yes. Okay. Now, we've done math first. Could we do chemistry first? Yes. We could do chemistry, then math, then English. We could also do chemistry first, then English, then math. Okay. Now, we've done math first. We've done chemistry first. What else could we do first? We could do English first, then math, then chemistry. We could do English, then chemistry, then math. So there it is. This is all your possibilities. 1, 2, 3, 4, 5. There are 6 possibilities for the order in which you can do your homework. Now, fast way to do this is to say, well, the first option, it's kind of like the first place, second place, third place prize. First option, second option, third option. Okay? How many options did we have for the first choice? When we got home, how many options did we have for first subject? Well, we could have done math, we could have done chemistry, or we could have done English first. So any of the 3 could have been done first. Now, after we choose the first subject, how many options do we then have for the second subject? Notice, if we choose math first, how many options are there for the second subject? There's only 2. Okay. After we choose math and English, after we choose math and then we choose our second subject, say we chose chemistry, how many options did we have for the third? We just had 1 option for the third. So this is 3 times 2 times 1, or 6 combinations. Remember, we are multiplying, not adding. Okay, do we call this independent or dependent? My question is, does the second choice depend on what you chose first? Yes, okay. If we chose math first, we can no longer choose it second, so this is dependent. Yeah. Let's look at question number 7. I'm just picking random questions off this page. You guys will do the rest of them. So number 7, well, actually your assignment is page P11, numbers 5 through 16 all. Okay, numbers 5 through 16 all. I will solve several of these on the board. Okay, number 7 says, a cafeteria offers choices shown in the table. How many different combinations of drink and salad are possible? So you have drink. You have, let's see, water, coffee, juice, and milk. And then you have salad. Okay, for your salad options, you have pasta, fruit, and chicken. Now, again, what you guys are doing is calculating the number of possibilities. In this case, over here on the problem number 5, we had 6 options, and then writing independent or dependent. This is question number 7. Okay, so drink and salad. You have water, coffee, juice, milk for your drink. You have salad, pasta, fruit, and chicken. Now, I'm going to diagram this slightly differently. Okay, so question, could we have water and pasta? Yes. Could we have water and fruit? Yes. Water and chicken? Yes. Let's diagram this. You can have water and 3 different options. You could have pasta, fruit, or chicken. Could you have coffee? Yes. You could have coffee and pasta, coffee and fruit, coffee and chicken. Okay. Could you have juice? Yes. Juice and pasta, juice and fruit, juice and chicken. What else? Milk. You could have what? Milk and pasta, milk and fruit, milk and chicken. So how many options do we have total? Well, you have 1, 2, 3, 4 drink options. You can have water with 3. Okay, water with pasta, water with fruit, water with chicken. You can have you can have coffee with pasta, coffee with fruit, coffee with chicken. Okay, so do you see that you have 4 options? Water, coffee, juice, or milk. And each of these options has what? 3 choices to go with it. So you have 4 options. I'm hoping you guys can see the multiplication. You guys 4 options for your drink, multiplied by 3 options for your salad. Okay, notice water, pasta, water, fruit, water, chicken, chicken. Okay, so we have 3 options, 3 options, 3 options, 3 options, making a total of what? 12 options. 4 times 3 gives what? 12. Notice you have 4 groups of 3. This is multiplication, so you have 12 options. Now, question, did our choice for salad, we have 3 choices for salad, did our choice for salad depend on what we chose for drink? No. If we chose a drink, for instance, juice, did we still have 3 options for salad? Yes, this is independent. These are independent categories, or mutually independent. Dependent case, okay? Or we call this mutually exclusive, Now, going down to question number 10. How many different outfits can be made if Jessica chooses 1 from each of 11? No, let's skip that one. No, let's go to number 8. Number 8. Okay, number 8 says, okay, Dane is renting a tuxedo for prom. Once he has chosen his jacket, he must choose from 3 types of pants, 6 colors of vests. So we have jacket, we have pants, and we have vest. Okay, jackets, pants, and vest. Jackets, pants, and vest. Okay, so it says once he has chosen his jacket, he must choose from 3 types of pants and 6 colors of vest. This is important for many reasons. This problem is something I need you to really focus. Okay, so notice. He has 3 options for pants, 6 options for vest, but it doesn't specifically tell you how many options he has for jacket. But it does say this. It says once he has chosen his jacket. So my question is, how many options for jacket does he have? He only has 1 option for jacket. Even if he has several options for jacket, he has to choose a jacket first before he can choose his pants and vest. So he has only 1 option for jacket because you're coming into the problem with his jacket has already been chosen. This is something students have a hard time seeing sometimes. There's only 1 option for jacket on number 8. It says Dane is renting a tuxedo for prom. Once he has chosen his jacket, he must choose from 3 types of pants and 6 colors of vests. So since he's already chosen his jacket, he only has 1 option for jacket. Okay. Now, he has a jacket. And so we're just going to ignore, this is going to be 1, well, here, I think we can just figure this out without diagramming here. Does his choice for pants depend on what he chose for jacket? No. If he chooses a jacket, he still has 3 options for pants. After he chooses jacket and pants, does he still have 6 options for vest? Yes. Now, it may not be a wise choice depending on whether he wants to match color, but the point of the matter is, if he's chosen his jacket, he still has 3 options for pants. Okay, maybe he has, doesn't have good taste, and so he chooses any one of the 3 randomly. But, so we have 1 jacket multiplied by what? 3 pants multiplied by 6 vests gives a total of 18 different outfits. Okay? So my question is, does the second choice, his choice for pants, depend on what he chose for jacket? No, this is independent. Okay? And lastly, we're going to solve one more. Number 11. Okay? Abby is registering at a website. Abby is registering at a website. This is number 11, so you guys can follow along. It says she must select a password containing 6 digits from 1 to 9. 6 digits from 1 to 9. Okay? 3, 4, 5. So I want you to put 6 spaces on your paper. Okay? She's choosing 6 digits from 1 to 9. My question is, how many digits are there from 1 to 9? Well, we've already established this. 1 to 9 has 9 digits. Okay, now, how many digits are there from 0 to 9? Hopefully you can say from 0 to 9 there are 10 digits. Okay, this is important for what's coming in this class. So from 1 to 9, she's got 9 options to choose from. So digits 1 through 9, there are 9 options for digits. Now, she's trying to create a 6 digit password. Okay? It also says how many passwords are allowed if no digit can be used more than once. No digit can be used more than once, meaning that if she selects a digit, she can no longer use that digit again. Okay, so how many options does she have for the first digit? Okay, hopefully you say, well, there's 9 options for first digit. Okay, for instance, if she chooses, say, a 7. Okay, now can she choose 7 for the next digit? No. Okay, so how many options are there for the second digit? The second digit, there are only 8 options, because since she chose a digit, she can no longer use that digit again. There's only 8. And how many options for third digit? After choosing the first and second digit, she only has 7. And how many does she have? 6, then 5, then what? 4. Okay, so we have 9 times 8 times 7 times 6 times 5 times 4. Okay, is this independent or dependent? Does the second choice depend on what she chose first? This is an example of dependent. Okay, now we're going to multiply. 9 times 8 is 72. 7 times 6 is 42. And 5 times 4 is 20. 20 times 42 is 840. So we have 840 multiplied by 72. Okay, just going to work this out. This is 0, 8, 16. 0, 8, carry the 2, 58. 0, 8, 14, 4, carry the 1, 10, 0, carry the 1, 6. Okay, so let's double check. 0, 8, 16, 0, 28, 8, carry the 2, 58, 0, 8, 14, 4, carry the 1, 10. Yeah, this is 60,480. So she has 60,480 possibilities. 60,480 possibilities for passwords. Wow. These things get large very quickly. So hopefully, again, page P11 tonight, page P11 numbers 5 through 16, you guys can figure out the rest of these. And I want you to, again, not only calculate, but also tell me whether this is independent, okay, independent or dependent. Okay, so calculate the outcome and then write whether this is an independent or dependent case. All right, great.